Welcome everyone. Much. So today we will continue from where we left yesterday. So just to make a recap, what did we do? So we defined the population risk as RW. So this is the expectation of loss with respect to data. We get the empirical risk. R and W. So this is the average loss on the training data set. And the training data is S Z1 to Zn. And then we wanted to bound the generalization error, which is RW minus R and W. We want to do this. And specifically, we were interested in the case where W's were obtained by solving some stochastic differential equation. And then for this, we defined so our main stochastic differential equation is dWt equals minus gradient. So I'm just going to call this F instead of, like normally we are trying to minimize the empirical risk, but I just want to make it like more general. So WT, and this will depend on the data of this function, plus some matrix valued function sigma. WT D lambda D L as alpha T. This is a rotational invariant alpha stable process in dimension D. So we argued this is a good proxy for stochastic gradient descent in practice when there are heavy tails. And I argued that when we define the image of the process, let's say W0 to 1, so I'm going to call this actually from now on curly WS, S meaning like this depends on, emphasizing that this is depending on the data set. As all the points W such that there exists a T in between 0 and 1, WT is equal to W. So I'm looking at the trajectory from time 0 to 1, and I'm putting all these points into the same set, curly WS. And so we argued yesterday that like looking at the worst case generalization error on this set makes sense because it is capturing the effect of the algorithm choice and the data as well. So it is kind of like a compact way of incorporating all the ingredients of the problem. Okay, so then I showed the theorem which essentially bounded generalization error over this set, like the worst case generalization error. And then with high probability, we wrote some terms. I can just write it again. Let me just write it quickly. This is alpha. I realized yesterday I forgot to write one detail here. So there's an L squared here. I'm going to tell you what it is. Plus I infinity, the mutual information between this set and the training set, plus log 1 over gamma over square root of n.
Can you remind us what B is?
Yes. So this holds with probability larger than 1 minus gamma. So B, we assumed that so let's just write it over here. So we assume N is uniformly bounded, and then I forgot this term L here. There's another assumption, which is for every Z, the function L is Lipschitz continuous on the L Lipschitz continuous on the first argument, and the L is uniform over Z. So we are assuming this loss function is Lipschitz, and the loss function is appearing. So the Lipschitz constant is appearing. Okay, so we argued that this is the case. Well, I might have forgotten some like absolute constants here.
Is the L square inside the log or
inside
outside?
the log? Okay, so the bound looks like this. I might have forgotten some absolute constant, but like the shape is just like what's written forward. So today I'm going to prove this bound for like a simpler case, and the proof is like very elementary, and then we are going to like this. I mean, I don't know if you are not familiar with manipulating things in this context. I think it might be useful, but it is simple. And then we are going to argue like how we obtain this bound afterwards, because I'm going to prove something simpler. And then we will discuss like what are the drawbacks of this, and then tomorrow we will try to get like better bounds. Okay. All right. So before starting, any questions at this point? So now let's start with this. So proof for the simpler setting. So in like one of the main difficulties in this, like proving this, is that the set that we are computing this premium over also depends on the data set, which is also random. So like everything depends on each other, and then like manipulating this supremum is not as easy as it could be if it didn't depend on S. So for proving, like for illustrating the proof, I will try to like isolate that difficulty.
You said.
Sorry?
Sorry, so S is random.
Yes, S is random. So this set is also random, depending on.
Yeah, so we have on the left-hand side of inequality is random variable, yeah?
Yes.
So it's probability whatever. On the right-hand side is a constant. This is a constant.
It's also random.
Also random because of
S is random.
I.
WS is random.
No, but this is
This is not random.
This is a constant.
This is a constant.
Yes. Yes.
So random variable is bound above by a constant of this type, yeah? Probability okay.
We have probability.
So like this is the probability here, but yeah. So I'm just checking. Like okay, so everything here is constant actually. Fixed. Okay. So to illustrate like how the proof works, I'm just gonna assume we have a curly W which is bounded. So I'm going to replace this with some W in a subset of RD, and then I will assume that it doesn't depend on S, so it's fixed. So to avoid this complication. And I'm still assuming like this two assumptions. And let's try to prove this for the case where this doesn't depend on S. So this will be our goal today. So more specific.
How can you be sure that it doesn't depend on this?
No. It depends on S. But I just want to illustrate how the proof works in case it didn't depend on S. So like to prove this result, we use some techniques, and the technique is quite similar even if this didn't depend on S. So like we need to do some covering and stuff like to appear there, like to introduce dimension. or to,
If condition is not satisfied, but you assume it.
so maybe let's
So
Let's
something
try it this
like
way.
this.
Simplify the proof to give us an idea of the proof.
Yeah.
Yeah.
Okay,
So
to
let's
assume.
say this is a problem, and let's forget about this problem. I'm defining a new problem.
Okay, new problem. Okay.
And then I'm going to argue the proof of this problem is going to be similar to the proof of this
Okay.
problem. This would be the argument. Okay, so more like precisely, we are going to prove an upper bound on the probability that the worst case generalization error is larger than some number epsilon. So we will try to upper bound this probability, and then this will automatically give us the bound that I wrote over here, like for the simpler case. Okay, so let's try to do this. So first of all, since we are assuming L to be Lipschitz, this means both R and R hat are also L Lipschitz, right? I'm almost sure. Okay. So then I can just continue. I can just use this property to simplify what's going on over here. So first of all, if somebody gives me two vectors W and W prime, then RB, the generalization gap for W, same thing, change the order. So I can add and subtract some terms, like the empirical risk for W prime and the population risk for the W prime. I can add and subtract. So I can just write this down as, so let's use two different colors here. So the generalization gap for W prime plus the difference between the empirical risks corresponding to W prime and W, and the difference between the population risks corresponding to W and W prime. Since R and R hat are Lipschitz, so this is like, we can just use the, like divide the terms, divide this thing into three terms. This is going to be smaller than L times W minus W prime. The same here, smaller than L times W minus W prime. So I can just write this down as, this is going to be smaller than the generalization gap corresponding to W prime plus 2L W minus W prime. So this is true for any W and W prime. Okay, so this is going to be useful for our purpose. And why is that? So our goal is to obtain some sort of dimension on the right hand side. So like, as we argued, like this is going to come from some fractal dimensions. Do you want me to like redefine, like define the, write down definition of the box counting dimension? Who doesn't remember the definition of the Minkowski dimension? Okay, I will choose a random person to tell me. I mean, Victor was not here yesterday, so I just want to write it for him. Just a reminder. Okay, so let's say F is a set in RD and bounded. Let's say N delta F is the set of balls which with radius delta, the smallest number of balls with radius delta to cover F. So this is the set of balls, and then this is the cardinality of this set. And the upper Minkowski dimension is defined as the link sup as delta goes to 0 log cardinality of this set of balls over log 1 over delta. Okay. So now let's keep this in mind. And what do we do next? So in the first lecture,
What is absolute value?
so it's the cardinality of the set. So n delta.
And
is
it's
the set of
it's the set,
balls.
not the
Yes,
number.
yes.
Not the
So yesterday I defined it as the number, but
Oh, yeah.
today I will change. I will need the other notation.
Okay.
So why? Okay, in the first lecture I showed the generalization bound for the case where this set W was finite, so we could use like some easy tricks. So my purpose now is going to convert this problem to that case to be able to use like this that simple argumentation. So in that case, like this was finite, set was finite, but in this case, like it is uncountable. So how can we do this? How can we convert this uncountable set, supreme or uncountable set, to maximum over some finite set? And the tool is going to be coverings. So what we are going to do is we are going to fix up delta positive, and then let's just cover this curly W with delta balls with the minimum number of balls. And then I'm going to put, as we defined over here, the centers of the balls in this set and delta F, and then for shorthand notation, I will just say n delta. So n delta is a set. It contains the centers of the balls.
Sorry. And delta of W, I think.
And delta of W. Yes. All right. So what does this mean? Since we have a covering, so for every W, we curly W, there exists a W prime in n delta such that the distance between these two vectors are smaller than that. Right? So it's guaranteed because we are covering with both. Okay, since this is true, then I can just combine these two parts. So if I can cover this set, if I cover this set W, and then if I use this property that the generalization error can be upper bounded by this term.
Should be two delta.
Ball
Radius T or diameter T. Diameter data, yeah.
the center of the ball.
Delta is diameter.
Delta is diameter, and then W prime is
The diameter is okay.
it's
Not radius.
diameter. Sorry, I said radius and let's say it's diameter.
N delta now means the centers, not the balls.
N delta is the center of the balls. Yes.
It is a collection of centers.
Collection of centers. I mean, conceptually they are the same, but then mathematically
Yeah.
it doesn't. The code doesn't compile. I understand. But any questions about like the syntax so far? I hope the semantics is clear. All right. So what does this mean? So then this means for every W in curly W, I can find a W prime in n delta such that the generalization bound corresponding to W is going to be upper bounded by the generalization bound corresponding to the center of the ball plus some error term. And then this is going to be bounded by delta. So this means now I can convert this supremum problem this was my original problem. I can convert it to a max problem instead of soup. Plus some error margin. Okay, so what is the interest of this? The interest of this is now this set is finite. So now I can try to manipulate this in a much easier way than before. Like this one was more difficult, but now this is much easier. So now let's now focus on the first term over here. This term. What is the probability that max W in n delta generalization gap is larger than epsilon? So I'm going to repeat the same arguments that I showed in the first lecture. What is the next step for this?
Replace max by sum.
Here, you mean?
It remains max by outside.
Oh, okay, so this is like 4 steps ahead, but true.
No, but it's for probability this is one step.
Yeah. Okay, so then this is equal to, there exists at least one W such that this gap is larger than epsilon. This is equal to the union. It's W in that delta. So the events, the union of the events, the probability of the union of the events is larger than epsilon. Sorry. The probability of the union of these events is equal to this. And now we can just upper bound this by the sum. W and delta. The probability of single events. Single case where this generalization gap is larger than epsilon. So I just follow the exact same steps that I followed in the first lecture. Super elementary. All right, so now since I assumed the loss is bounded, we can apply Hoeffding's inequality over here. Therefore, this is further upper bounded by some W in and delta 2 times exponential minus n epsilon squared over b squared. And this doesn't depend on that W anymore. Hence, this is going to be equal to the cardinality of n delta times x, the same quantity. Okay, so can you see where I'm trying to go from here? So now we have some like covering number appearing here, and then I said like the dimensions covering number. So I will try to link all these things together to get a bar. So what I'm going to do now to simplify some notation, I'm going to define this as gamma. And then this means if I just set this to gamma and then solve it for epsilon, then epsilon turns out to be b times log 2 and delta. It's inside the log plus log 1 over gamma over n. Okay, Okay, so it already started looking like the theorem that I wrote. So what does this mean? So what we have proved so far, we proved with probability at least 1 minus gamma, the maximum error that we will do on the center of the body is going to be smaller than this quantity. So 5 square root of 4 2 cardinality of n delta plus log 1 over gamma over. So we have proved this. Okay, so what's next? What we will do? What should we do? So the next, as a next step, is there any question about like until this point? So as the next step, I want to combine this and connect this to the upper Minkowski dimension because like there is this covering number appearing. I want this Minkowski dimension appear in this bound instead of the covering number. Okay, so for this, like to be able to do that, so now I'm going to go into this like context. I will choose a decreasing sequence of delta n's. So this is like 0. And then I choose this as an, I index it by n on purpose. So I will make this delta go to 0 as we increase the number of data points. And then this means for every epsilon, so this time I'm going to use a different epsilon, there exists some n0 such that n larger than n0 implies the log covering number is smaller than the Minkowski dimension of W plus epsilon times log 1 over delta n. So let's denote this by dm. Okay, now I can use this bound over here. So it's almost done. But before that, I'm going to choose the specific delta n to be able to cancel some terms. I'm going to choose delta n to be equal to 1 over square root of n times L squared. And then with this choice of, and then I'm going to choose epsilon, this small, like the other epsilon, to be equal to dm itself. And to like simplify the like the terms. And then under this choice, this means for large enough n, we have that log 2 cardinality of n delta is smaller than log 2 plus dm log n L squared. So I just like simplified some things, and then this is going to be useful for another reason, which will come in 1 minute. Any questions? I see some confused.
Choose epsilon to be dm. I mean, dm isn't, I mean, is it?
It's fixed, right? So we know it's finite. We chose it like to be a bounded set. All right. So now almost the last step. So one step before the last step. Combining all these things with this step. So we go back to this step. So now this is going to be our original object to analyze. This means Maybe I should clean up some parts. Don't need something more. Okay. So going back to the original problem, now we have with probability larger than 1 minus gamma. The supremum, like the worst case generalization error on the set per W is smaller than B times of 2 plus the Minkowski dimension times log n L squared plus log 1 over gamma over square root of n. But then we made some, like we put some margin of error because of this discontinuity. So now there's an additional error term, which is 2 times L times delta n. But then we chose delta n in this way. Therefore, this is going to be equal to 1 over square root of n. How did I manage to do this?
So what did you write in this fraction?
Sorry?
Root of n I can see in 2 over.
So 2 over square root
It's
of
2. 2.
this is 2.
Okay, believe me, it's 2.
Okay. So what we have proved so far, almost done. So the supremum, like the worst case error on the set, is going to be smaller than like this quantity plus some error term for n large enough. So we had to use n large enough over here already. So we don't really know like how large n should be, unfortunately. So at this point we have nothing to lose. We can choose n even larger. So to simplify some terms. So first of all, this is a constant. This term increases with n. So there will be n large enough such that this is going to be dominated by this term. So this term goes to 0 faster because it's square root of n. But then this is going to 0 slower because log n over n, square root of log n over n. Therefore, there will be large enough n such that like this term is going to be dominating like all the other things. Therefore, we can just write it down as for n large enough. This is going to be smaller than 2b. The Minkowski dimension is log NL squared plus log 1 over gamma over n. And that's for n large enough. Okay, so this is the generalization bound in the case where W doesn't depend on the dataset S. Any questions?
You can put any number bigger than 1 instead of 2. Yeah?
Sorry?
The factor 2 at the beginning. You can put any number instead of bigger than 1. You say 2 times b, but instead of 2, you can put 1 plus another epsilon.
I'm not sure. Yeah, I mean, like I'm just choosing like to simplify things. I'm gonna say okay, for n large enough, this is going to be dominated by this. So there's a 2 coming here to get rid of this. Then this term is going to be larger than this. Then this is multiplied by square root of 2 again. Then 2 goes outside.
You will replace 2 by any number bigger than 1.
Maybe. So we can make this maybe more tight. Yes.
That's what I say.
Any questions? Any other questions? Okay, so what is the moral of the story? So we said if this W doesn't depend on the data set, then we can obtain the dimension of the set, the Minkowski dimension of the set over here, instead of the ambient dimension, like the number of parameters D, right? So like if this set is bounded, we immediately have this relationship. So this bound says that at least, I mean, if you're increasing the number of parameters in your model, this bound doesn't necessarily increase because like the implicit dimension, the intrinsic dimension might not increase. So this is the take-home message of this bound. So I'm not going to prove in the case where this depends on S because it's not difficult, but it's like very hairy, so you need to apply a lot of rules and like keep track of a lot of terms. But the main tool here is that, like, if you remember, in the case where the curly W depended on S, we had an additional term which was the total mutual information between WS and S, right? So this bound doesn't have this. And the reason is, in the proof, to be able to deal with this dependence, we use this simple lemma.
Just like, so if there is no dependence, the mutual information is zero.
So there is a simple lemma. This can be tracked by Kemp's paper. So let's say X and Y are random variables. So E is any Borel set on the product space. Then the probability of this, the measure of the set under the joint distribution is smaller than exponential of the total mutual information between X and Y times the measure of B under the product of the marginals. So you can take any joint distribution and then you can decouple it by introducing this additional like multiplicative factor, and then at some point in the proof, like we use this, and then we obtain like the additional term is coming over here. All right. So now what we have proved, we just proved that for any set W, like for any bounded set W or like WS, we can obtain some generalization bound like this, which includes some fractal dimension. So now I want to connect this to like heavy-tailed stochastic differential equations. And to do this, we are going to use an existing result from 1998 or 88, something like this, from René Schilling. And we will put some assumptions to be able to use it directly. So like the rest of the result is going to be directly taken from the existing work. So let me just briefly describe what the result says, the result that I mentioned, and then I will just cite it properly. So the reference is
So yesterday you said you're going to use Blumenthal and Gator, right? Or am I mixing
I
things
wanted
up?
to show it as a motivation to illustrate that like the topology can depend on details. But then for this specific case with the stochastic differential equation, it's not as simple.
Okay.
So I'm going to
understand.
use something else.
Okay.
So the reference is Schilling, Philip processes generated by pseudo differential operators. Operators on the Hausdorff dimension of their sample path. It's 1998. I'm pretty sure they didn't write this paper with the hope that it will be useful for machine learning at some point, but it was super useful for us.
Joe,
I don't know it. I didn't write it in my notes. Archive, I don't know.
okay, didn't exist.
Really?
It's not in this century.
Okay, so the theorem essentially says this. And I'm going to translate it to our setting. So let's say we have a feather process. And then we have, and then this field is defined by a symbol. It is symbol psi, W and Z. Psi. I'm not going to define all these things, so like I need to have made a job to. This is right. So this is like this symbol. Okay, so the theorem says this. So if there exists a W star such that when I freeze this symbol at this point and define a Levy process with the characteristic exponent like this. So I freeze this symbol at some point W star, and then I use this as a like a Levy exponent. So this is going to define a Levy process, and I define the
TMS.
Transactions of the AMS.
There's a difference between these two.
And journal chart.
Theoretical probability.
But actually.
Theoretical probability.
Yes.
I think this is the general theoretical
So
probability.
Journal chart.
Then,
Jeff?
under many technical assumptions on this remainder term,
Jeff field now, yeah.
I will write all of these things. So they are mostly like integrability assumptions.
He's like you. 20 years usual theoretical probability. You know what, Jeff?
So let's say the process, the feather process defined by the symbol, let's call it like xt. So the Hausdorff dimension of the image of x for any t is smaller than let's call it beta. And beta is the upper Blumenthal Getter index of this Levy process. Beta is defined if
What is it?
what does, so this is almost fine. Okay, so it doesn't look anything related to machine learning, I agree. But then what does it say?
Is the infimum over alpha or over lambda?
Lambda. And then this is lambda. There's no alpha in this case. Okay. So what does this say? Let's say we have a feather process, and then we freeze this feather process at some point, and the symbol gives us a characteristic exponent for the Levy process. And if the remainder term satisfies certain assumptions, we can link the Hausdorff dimension of the original Feller process to the upper Blumenthal getter index of the Levy process defined by this symbol. Exponent, sorry. So this is the theorem. And then how do we apply this to our case? So let's translate it to our case. So this essentially requires, so there will be some point such that the Feller process behaves like the Levy process defined by this exponent, and then it doesn't change much. And the much, like, doesn't change much is made rigorous in the assumptions. So what was our process? This is our initial process that we were interested in. So we can think about this assumption like a condition like this. So let's take W star to be a local minimum. So let's try to link it to machine learning of F. Then gradient of F at W star will be equal to 0. And then by freezing the, assume this is Feller. By freezing the Feller process at this point will give me a Levy process. So let's say W prime, dW prime T will be just sigma W star D. This. So now this is going to be a Levy process. If let's assume that this is like the function at W star is positive. Okay, so then what these assumptions essentially imply, around this local minimum W star, if these two processes behave similarly in the way described by the assumptions, then we can relate the Hausdorff dimension of this process to the index of this simpler Levy process. Okay, then in this case, we can compute beta in closed form. So the upper Blumenthal getter index of this process, if you have this like here this matrix positive definite, beta will be equal to half. So that's why, okay, so like in this case, we can reduce these computations to this identity. Any questions before I, yes?
So in particular, you don't really need that L alpha is stable, right? Could be locally stable or something like that.
True. You
So
just need to
you don't
compute
need
this.
the similarity, just the Blumenthal getter index.
True, but the thing is, when we were writing this paper, I had already written some papers where I argued that this is good. So then this would be,
Okay.
like, to be completely honest. Yeah. And you had a question?
Yeah, I'm just wondering about how you make the argument. How you related the two SDEs? Can I, like, each time, like, you have to, I mean, how do you relate the two SDEs?
So like, you need to look at this paper. So like I cannot really say anything about how it's proved. Like it
Just the dimension, right?
Yeah, no, this is a phrasing argument, right? I mean, you phrase it at some point and you put the division.
But then I mean, so like for Hausdorff dimension, you can use some like moment estimates for the process and etc. And then this plays role. So I cannot say it from the top of my head, but well, it's written in this paper. So it's not our contribution at all. Okay, so then what's missing? So we proved a bound which contains a Minkowski dimension. And then we argued, like by using this paper, we can get an upper bound for the Hausdorff dimension of this process. So the only link missing is, like, I mean, Hausdorff dimension and the Minkowski dimension, they don't need to be equal to each other in general. So now, how much time do I have? So maybe I should wait a bit more because after I write this, I'm scared of getting a lot of questions. So then we put this assumption. So the Hausdorff dimension of the sample path of this process We assume that it's equal to its impossible dimension. So then we can directly use this estimate into this.
So for Levy processes, there are results that say that the upper or lower Minkowski dimension equals the Hausdorff dimension.
So then it means everything is equal. But then this process is like more complicated. So it's a good point. So like for the simple, like alpha stable processes, it holds, it's true. But then when you put like a drift term like this, then it is not guaranteed that it's going to hold. So we assume the drift is nice enough such that like the topology doesn't behave very weird. Okay, so now combining all of these things, as a result, we obtained the bound that I described yesterday. Any questions? Other questions?
Did you ask Schilling to prove this identity?
Sorry?
Did you ask Schilling to prove the equality in your assumption? Like this could be an interesting open problem for probabilists to prove, right?
I mean, so, well, I didn't know him, so I still don't know him, but.
But isn't he a colleague of Anita?
Yeah, maybe.
Yeah, he is, yeah.
I mean, we wrote this paper and then he immediately sent us an email saying that thanks for like citing my paper, and then we apparently made mistakes in the reference, so we just.
So were you the first who cited it?
No, but I'm usually like a bit, I don't know, intimidated by papers like this, so I'm scared of getting too close. But yeah, I mean that would be interesting.
I have a general question. When you impose assumption on the drift, how do you know that it's
Very nice guy, actually.
practical application as machine learning?
Which assumption do you mean?
Because you said that
You mean this
Yes.
one? I don't know. No, but that's a good point. And then tomorrow I'm going to write down more like different bounds, and we won't have this problem. Actually, okay, I think it's a good point to discuss like what are the problems of this approach. If I can find my notes.
We can start addressing in the next couple of weeks.
Huh?
That some of us will try to address in the next couple of weeks.
Okay, so like what are the problems of this bound? First of all these assumptions are not really transparent. Assumptions. We don't really know like what they really imply. The second problem, we have this like annoying mutual information term. And in general, we also don't know how this behaves. So it is impossible to compute. So another problem. So we assume that the loss is Lipschitz. So this can be problematic for us, like in neural networks. Like this loss not Lipschitz, so like the Lipschitz constant is infinite. So then, like, how can we deal with this case?
Is that like locally or because globally it's not Lipschitz?
Globally not Lipschitz, locally
Okay.
Lipschitz, yes. And then, yeah, so like these are the problems. So tomorrow I'm going to describe another bound which hopefully address these 2 points, but then it will also have like some other problems, obviously. And then this one, we already proposed some solution. So here we assume Lipschitzness and then we use the covering argument. If we didn't assume Lipschitzness, we could just define a semi-metric. So for 2 points W and W prime, so here we use the poles where the underlying metric was Euclidean metric. This was the metric. But I can just define a new semi-metric, which depends on my data. So I can just define it like this. WZI minus LW prime ZI. So given a training set, I can say these 2 points W and W prime are close to each other if they are giving the same loss on every data point. So I can define a metric like semi-metric like this. And then I can cover the space by using this metric instead of Euclidean. And then this approach eliminates the requirement of the Lipschitz loss. So we don't need it by using this. And then this one is published last year. We this and myself. And one last comment about this framework is that to be able to link generalization to heavy tails, we took kind of like a long path. So we first linked it to fractal dimensions and then used another link. So tomorrow we will try to directly get a bound based on the, like just attacking the problem itself without introducing intermediate steps. But on the other hand, linking the problem to fractal dimensions opened us some like more directions actually. So we could link this generalization bound to some like computational algebraic topological approaches like persistent homology. So I'm not going to go into detail of this. But the nice thing is like you can try to compute our bounds by using like topological tools like this one, and then it's also written in this paper. Okay, I think I'm going to stop here. Let's take any last question.
Yes. Introducing this metric or using this metric that you write on there, does that not produce any trouble then with these dimensions?
So the dimension is going to be defined with respect to this metric.
Yes, but then, I mean, that's Schilling's result still.
So you cannot
I'll-
get to heavy tails anymore.
Yeah.
Then you just look at this, and then you get a fractal dimension later on, and you stop there.
You don't know how to
Yeah, so
control
then
the
heavy
fractal
tails
dimension.
will- So we change this metric to this, and then in this paper, the proofs became like 10 times longer. It was like super like disgusting and like so many. And then Benjamin, my student, he discovered like do this like so much easier way. So we wrote another paper like going to this one. The proof became like 2 pages. So if you want to discuss, we can also discuss it. Well, thanks for listening.